So 7.1, we're looking at the exponential function itself. So basics real quick about an exponential function. An exponential function, let's say f of x, so using our function notation, of b to the power of x, where b is a number. So a positive number not equal to 1. So I have that b has to be greater than 0 and b cannot be equal to 1. These are the constraints that we have. The big idea to take away from this, though, is with our exponential functions, the base is going to be an actual number and our power is the exponent, which is the reverse of what we saw with like the quadratics. With a quadratic, we would have x squared, right? And so our base would be a variable and the power would be the number. With the exponential functions, it's the opposite. The base is now a number and the exponent is the variable. So I have an example of an exponential function would be f of x equals 2 to the power of x. So or 1/2 to the power of x or 17 to the power of x, something like that. When our base is greater than 1, we have, so if b is greater than 1, we call it exponential growth. And we can see that from the graph. So again, if your base is bigger than 1, so even just 1.1 or 50 million, any of those fall into the category of exponential growth. And you see by their graphs, right, if I plug in 0, anything to the 0th power is 1. So all of these exponential functions, if it's the basic one, I didn't add, subtract, or anything like that, then what we call the parent function will cross through 0, 1. And as our x values get bigger, the y values go up to infinity, right? So it's exponential growth because it's growing exponentially really, really quickly. So again, if our base is larger than 1, then we have what we call exponential growth, and the graph will take on some sort of shape like this. Now, if our base is less than 1, in between 0 and 1, so something like 1/2 raised to the power of x. And so this is just an example, but this is for all of the exponential functions that are in between, whose bases are in between 0 and 1. So any fraction in between 0 and 1, a third, 4/5, anything like that, we have what we call exponential decay. So something is still occurring very, very quickly, but now instead of it getting really big really, really quick, it's getting small really, really quick. So all of those graphs, again, still anything raised to the 0th power is 1, so they all of the parent functions, without any transformations, I didn't go up, down, left, right, anything like that. These are all the parent functions. If I raise them to the 0th power, we have the property anything to the 0th power is 1, so we know we have a y-intercept of 0, 1. But now, like I said, we have exponential decay. So as the x values get bigger, usually they're representing time. So as time goes on, whatever this value is representing is getting smaller. It's decaying. So we have this right here. Now, as this thing gets smaller, you think about, so this is actually representative of what we call half-life, and you'll see that in a couple of sections when we talk about applications. But half-life of a substance, let's say anything, carbon, something like that, if you put it on the counter and let it sit for a while, eventually half of that substance will have decayed, right? And so you wait that time again, and what was left, half is gone, and then half is gone, and half is gone, and so on and so forth. So if you keep taking away half, there's no way that you could have negative substance left, right? But if I keep taking half, keep taking half, keep taking half, the value that I have left is getting smaller and smaller and smaller, closer and closer to 0. And we can see that on the graphs, that as time goes on, the value that we have is getting closer and closer to 0. It'll never equal 0. If all I'm doing is taking away half each time, I can take half away for an infinite amount of time and it never be equal to 0. It just skates along and gets ridiculously close to 0. So anyways, this is my rant about exponential decay. So this is what the graphs look like. You do have graphing utilities at your disposal. Even if you don't have a graphing calculator, a good website to go to is desmos.com. It's an online graphing calculator that allows you to type in any function and it'll graph it for you, so you can get an idea of what these graphs look like. And we did talk about transformations before, and so you can kind of remember, if I subtract 1 from x, what does that do to the graph? Desmos is a good tool to help you see exactly what is going on. All right. Another big part of 7.1 is solving some exponential equations. So there's there's 2 different methods to solving exponential equations. We only have the tools to use one method right now, and it's called the one-to-one method because it uses the one-to-one property of exponential equations or exponential expressions. So what the one-to-one property tells me is if I have some base raised to some exponent, and I know that's equal to the same base raised to some other exponent, then what must be true is that those exponents are equal to each other. So if I can get in my equation the bases to be the same, then this property will hold and I'll know that those exponents are then also equal to each other. So let's look at it in a little example real quick. So very small one. Let's say I have 3 to the power of x equals 3 to the power of 5. And I want to solve this equation for x. So we see that already I have a base on the left, a base on the right, and the bases are the same. So this already falls in line for the one-to-one property. Since it already holds, then I know my exponents must also be true. So I can take my exponents and set them equal to each other. This one's already solved for x, so I know the answer must be that x is equal to 5. Now, of course, they'll be a little bit more intense than that. And the bases may not automatically be the same. So let's look real quick before we solve another equation. Let's look at how to change one base to another base without changing the value. So let's say that I have a base of 1 over 25. And the base that it's equal to is 5 to some power. And so I'd want to rewrite this exponential expression with a base of 5 without changing the value. So think of what do I raise 5 to the power of that would give me 25? And the answer is 2. 5 squared gives me 25. But this is 1 over 25. So what could I do to the exponent that would make me flip that value over? The answer should be make it negative. So I could rewrite 1 over 25 as 5 to the negative 2. I didn't change the value because if we simplify this back out, I know 5 squared is 25. The negative tells me to flip it back over, so 1 over 25. So I didn't change the value, I just changed the way that it looked so that I could have a common base, so the one-to-one property comes into play. So let's use that tactic right here in actually solving an equation. So let's say that I have 2 to the power of x minus 3 equals 1/8 to the power of x plus 2. Alright, so I want to solve this exponential equation. In order to do it, the only tool that we have is to make a common base so we can use the one-to-one property. So I have a base of 2 and I have a base of 1/8. So I see automatically that if I do 2 to the third power, that does give me 8. So I could leave this 2 alone and just focus on this base to rewrite it with a base of 2. So I already stated that 2 to the third power gives me 8. 2 to what power would give me 1 over 8? -3. So 2 to the -3 would give me 1 over 8. So I could rewrite 1 over 8 as 2 to the -3 power. And that is still raised to the power of x plus 2. And on the left, I still have 2 to the power of x minus 3. And so now I pretty much have a common base. I do need to use some of my exponent properties to see what my exponent actually is. Notice here that I have power to a power, and the property, the power rule, tells me to distribute those powers. So I have to do x plus 2, all of x plus 2 times -3. So when I distribute that exponent, I get 2 to the power of -3x minus 6. And then I still have that equal to 2 to the power of x minus 3. And now I have it set up for the one-to-one property. I have a common base set equal to each other, and by that one-to-one property, I know then that the exponents must be equal to each other. So I can now take the exponents, set them equal to each other, and solve the equation. We end up here with a linear equation, which we looked at a while back. So we should be able to solve this for x, get all the x's on one side, all the plain numbers on the other side. So I'll add 3x to both sides, and add 3 to both sides. So 1x plus 3x gives me 4x, 3's cancel, bring down my equal sign, 3x cancels, -6 plus 3 is -3. And now to get x by itself, I'll divide both sides by 4. So I end up x equals -3/4. And there's our answer.